Welcome back. In my previous video, I gave you a bit of history on random forests and bagging and described how they worked and showed you how we could fit one in R. What I want to do in this video is to talk about some of the ways that we interpret these random forests. So, um, in particular, I'm going to talk about three things. I'm going to talk about out-of-bag estimates of prediction error. I'm going to talk about variable importance plots and partial plots. So let's start with out-of-bag estimates of prediction error. One of the big benefits of random forests and bagging, for that matter, is that it's extremely easy to get an out-of-sample estimate of your prediction errors. And so to understand how this happens, you have to remember how bagging works. Okay, so bagging and random forests draw a sample with replacement with the data. Okay, so let me just illustrate a sample with replacement from this data set, which consists of the numbers 1 through 10. So you can try this at home if you want to replicate this. And so I'm going to say, give me a sample of size 10, and I want you to replace the numbers after you pull them out. So you see, first we pull out 3, then we pull out 10, then we pull out 8. Oh my goodness, then we get 10 again, then we get 8 again. And in fact, there's a theorem that shows that roughly 1/3 of the numbers will not make it into the sample. Roughly 2/3 will. Now, we're only using that, the roughly 2/3. It's not exactly 2/3, but it's in that ballpark. We're only using that to train our model. And then, okay, I go down, I draw another random sample, and you're going to see this time we got 1, 8, 7, and you'll see 2 and 5 get omitted. 2 and 5 were in this previous sample. Actually, 2 was, 5 wasn't. And if we repeated this again, we'd get different 7 or so numbers that come into the sample, and a couple of them come in multiple times. Like it looks like 9 comes in twice here. Well, Leo Breiman had a very clever idea, which was, why don't we use the left out cases as a test set? So, we're not using them. Why don't I just, after I estimate my model using, the sampled training set, I will apply that to the left out cases, and it's like I've got a test set, all right? But I get that test set without having to, use k-fold cross-validation, without having to set aside a big chunk of my data that I can't use. This chunk that I've set aside happens kind of naturally. So what you need to know then is that this is kind of a free way to get an out of sample estimate of training error. Let's go back to my defaulting customer example. So remember, we had a database from a health club, and these health club members were churning within the first 3 months, and so we want to be able to predict whether or not they churn in the first 3 months as a function of how much money did they put down, what was their gender, what was their age, how much were they using the club, and how were they paying the bills. So I don't want to go into detail on that. You can go back and look at some previous videos on that. But I just want to point out a few things. The use variable has some missing values. And so I'm going to set use, whenever use is missing, equal to the value minus 99. And so trees will isolate this value if it has a different effect on the dependent variable. Otherwise, you might get something like use less than 2, and which would include missing 0, 1, and 2, or less than 2 would not include 2. But that's one way to handle those missing values. I actually logged the down payment value. This would help if we wanted to look at some partial plots to interpret it. Of course, trees are robust to monotonic transformations of inputs. And so whether I have a tree splitting at down payment equals to 100 or the log of down payment base 10 equal to 2, they're the exact same split. So this was not really necessary, but if we wanted to look at this with a partial plot, it would help things. All right, well, I'm going to go load up random forests, and I'm going to build a quick random forest model. One thing to note, the previous model that I showed you in my other video was a regression tree problem. By using the factor function on the left-hand side of this formula, we tell R that we want to fit classification trees. So this is it's actually a 0-1 variable. And by default, R would try to fit a regression on that, and you don't want to fit regression trees on a 0-1 variable. You're better off treating it as a factor. All right, so I went off, I fit my tree model, and when I display the output, what I want to point out, we get the usual summary of here we built, we used 500 trees. We actually used 2 variables in every split. Where did that come from? Well, for a classification tree, we're going to take the square root of p. So 1, 2, 3, 4, 5. We had 5 variables. The square root of 5 is a little bit more than 2. So we round down and take 2 variables at every split. And remember, that increases the randomness of our algorithm. The next thing that we see is the OOB estimate of the error rate. So that's the out-of-bag estimate. And so think of this as the misclassification rate. R has also given us the confusion matrix on the held out data. So what we have in the rows are the true classes, and what we have in the columns are the predictions from the model. On the last column, we see the classification error, and so this is conditional on the true class. I've gone down and shown the math with prop.table. So the way to think about this number right here is this is the false positive rate. So 3% of the true negative cases are falsely classified as positives by our model. This, on the other hand, is the false negative rate. So 56% of the cases that really are positive were falsely classified by our model as being negatives. Second topic, which is variable importance. So I'll just say that this is kind of an active area of research right now, and I'm only going to talk about the variable importance measure, one of the variable importance measures that Breiman mentioned. Here's the basic idea. I'm building a lot of trees, and those trees all involve many splits. Now, every time there's a split, different variables can enter into that split. Now, an important variable will tend to enter into the splits more often than a variable that has very little relationship with y. So if you have an important variable, it's going to enter into a lot of splits. And remember I guess it would be earlier in this week, we talked about looking at the change in the residual sums of squares at the change in impurity. Okay, so the change in the residual sums of squares is just the reduction in RSS that you achieve with every split. So we called it delta RSS back when I covered cart trees. Well, what we could do is simply keep a running total of what is the change in the sums of squares that is due to each variable. So if a particular variable comes into the tree very often, it's going to be responsible for a lot of reductions in your SSE or your Gini coefficient, whatever your impurity measure is, and we want to keep track of that. So notice if you use the importance function in R, it's going to tell you a measure of how much this variable explained in our trees. So notice the down payment amount is the most important variable. So that's the one that is coming into a lot of trees and reducing our Gini coefficient of measure of impurity more than any other variable. Payment type is the second most important variable. You can see that gender comes in dead last. We found some minor differences with gender when we fitted some logistic regressions, but it's pretty small in the grand scheme of things when it comes to things like the down payment, the payment type, and the use. Those are really powerful predictors. Another thing that you can do is use the var imp plot. This is in camel case, so you've got a capital I and a capital P. That's a very confusing thing to a lot of students. And when we look at the var imp plot, all we're doing is plotting what we just saw in that table. It's often easier to visualize it, and everything's been sorted for you, so the most important variable is at the top. So that's a very useful measure. I now want to give you a bit of a caution with these importance measures. So let's go back to the Washington, D.C. bike sharing data that we analyzed with the Generalized Additive Model lecture. And so I brought this in, and remember, we're predicting the count of the number of bicycle rentals on every day over a 2-year period as a function of the date, the calendar month, the weekday, and the weather conditions. All right, so I brought up random forests again, and I'm going to fit a random forest using, I think this is all the variables. I may have left the raw date variable out. Anyway, I've just dumped everything in, and we have our random forest regression model now. And let's go look at our variable importance plot. And so clearly, year is the most important variable. This was right after they launched the program, and in the first year demand wasn't that great, and in the second year it increased substantially. So that turns out to be the most important predictor coming into these trees. You're going to see the next two most important variables are temperature and adjusted temperature. I believe adjusted temperature might take into account the humidity level. And so these are, kind of a close second and third. Well, maybe not that close to year, but they're definitely second and third. The next most important variable is the season out of the year, and that's far less important than those two. But I want to point out the correlation between temperature and average temperature is about 0.99. So these variables are basically copies of one another. Not quite exact copies, but they're highly confounded. So back when we studied linear regression, we talked about the omitted variable bias and multicollinearity. And what we saw was if you have two variables that are highly correlated, they can kind of serve as surrogates for one another. So if you get rid of one of them, the other one becomes more important. We studied the omitted variable bias theorem, and it's like the other variable picks up the slack when one variable drops out. And so we should expect that to happen in this case. So if I get rid of a temperature and just keep temperature in the model, we should get roughly the same fit statistics, but temperature ought to be much more important. So I'm just going to go back and show you our training R squared back here was about 88.08%. When I get rid of a temperature, I want you to note R squared actually goes up. So I'm not sure if there's a tiny bit of overfitting going on. I tend to doubt that. It's hard to overfit with random forests, but you know, we've actually improved our training set air by getting rid of atemp. Now, notice my variable importance plot gives me, I'm going to say, a pretty different story, because in the previous plot, it was year was the dominant predictor, then these two temperature variables were sort of in second and third place, but quite a bit below. Now, temperature is the most important variable, and year is kind of a close second. So the point I'm just trying to make with all this is, you know, you take these with a grain of salt. So the way I wrote it up here was interpret them with some healthy skepticism. When you have highly correlated predictor variables, just as with regression models, they can you know, serve as surrogates for one another, and you're going to get, you know, very unstable regression coefficients in that case. And likewise, the variable importance measures will be unstable. So, all right, the last diagnostic, or maybe it's not a diagnostic, but an interpretive device, is to try to understand how does one of the variables relate to y. And so really what we're trying to do here is get something like a regression or a GAM where you can actually see or describe, you know, how does a change in x sub j relate to y. On the one hand, I think I kind of prefer linear models and GAMs for this sort of thing, for some reasons that I'll explain in a minute. But you know, these measures are out there, and you should probably know about them. So once again, this is a very active area of research, and there's several methods that are available. So I'm going to talk about the partial plot method, which is available in the Random Forest package. I'm also going to talk about a brand new method. This method hasn't even been published as of May 13th, 2020. It's actually just been accepted for publication, and so it should be in print in a matter of months. But that's how new this method is, and it has some clear advantages over the partial plot. So I thought I would talk about that here. I don't plan to go into detail on how these methods work, and I refer you to an ebook that you can click on if you're interested in the details of this. To start this discussion, let's go back to the GPA data set that we studied back when we did generalized additive models. So here was my code. We know the grade point average for a bunch of students at some college. We know their verbal and math standardized test scores at the time of admission. Okay, so what we'd like to know is, how does the verbal and math GRE, or this would probably be ACT or SAT, how do the you know, those standardized test scores predict performance in college? So you could kind of think about, should I pay attention to those standardized tests? Are they predictive of anything? This would be something called predictive validity in the social sciences. So a measure has predictive validity if it predicts some subsequent outcome, like how you do in college. So you could think of us evaluating the predictive validity of these test score measures. Kind of a controversial subject, you know, should we pay attention to these test scores? Anyway, I went off, I fitted a GAM with a spline on each of these terms, and then remember, you can just plot a fitted object from a GAM, and you get the partial plots. So these partial plots describe how changes in either one of the predictor variables are associated with a change in your grade point average. So as your verbal score goes up, your grade point average goes up until a point, and then it seems to go down. I think this data set was cooked. I think I mentioned that in the previous video on GAMs. When it comes to the math score, the effect is maybe a little bit weaker. So I have comparable scales on my y-axis. So remember, I emphasized the importance of setting that scale parameter. But what you have is just an increasing relationship that flattens out after a certain point. All right. Well, we could also analyze this data set with a random forest. So I went and estimated a random forest on it. And we can use this partial plot command. So the way partial plot works is you give it the fitted random forest object. You can also give it a gradient boosting object if you want, but we haven't talked about that yet. That'll be the next video. You give it the data set that you want to evaluate it on, and then you put the variable name in quotes. And so what you'll see is a story that's fairly similar to what we got with the GAMs, but they're a little more jagged. I kind of prefer the splines. The other thing I really like about the splines is that it's very easy to get 95% confidence bands for the mean predictions. So that kind of gives me a sense for how reliable these estimates are. So for those reasons, and one more that I'll discuss in a second, I really prefer using a GAM over this partial plot. So I want to just introduce AL plots, and I want to give a shout out to one of my friends and colleagues, friend and colleague who's Dan Apley. Professor Apley's a professor at Northwestern, and he created this AL plot method, and it's as I say, it's about to be published. And it's already been written up in that ebook that I referenced earlier, and it has a lot of desirable properties that the partial plots don't have. So in order to use Professor Apley's function, you have to define a prediction function that basically calls up predict, but it changes the names. So x.model is the name of the fitted model, and then you give it some new data. This is the command to generate an AL plot. It's a little bit more complicated than the partial plot, just slightly more complicated. We give it the data set name, we give it the fitted object, we have to give it this predict function. Then we're going to specify which variable we want to study. And so this is going to correspond to the columns in the GPA data set, so whatever data set we specified back here. So when I say j equal to 1, what that means is I want to look at the partial plot for the first column, and then I call up my function again and I say, well, let's go look at it for the second column. So this will be for verbal, this will be for math. And his plots are not quite as jagged as the partial plots, and there's some theoretical properties that are more desirable. These do a better job when you have correlated x's. All right. I want to close with a caution, and so I've just put the caution in boldface here. So partial dependence plots are misleading when interactions are present. So let's take a look at a function that I gave as an example during the Generalized Additive Models lecture. And so this is just a product of two x's. I've assumed that the domain is from -1 to +1 on these x's, and this is called a saddle function. So we can go examine what a saddle function looks like. So you could think about, I'd sit in the middle, I'd put my legs down here, and then my back is here, and here's the front. So what's really important to notice about this is when both of my x's are positive, the product is positive. When both of my x's are negative, so think about this is 0, this is 0. When they're both negative, then of course the product's also positive. When exactly one of the two is negative, it goes down. And so what makes this such a difficult function is that the effect of x1 on y depends on the value of x2. So it's real easy to see that if you take the partial derivative of y with respect to x1, you see that it depends on x2. And so when I look at this plot, as x1 increases and x2 is equal to +1, then the effect of x1 on y is positive and increasing. However, if x2 were equal to 0, you're going to see that the effect of x1 on y is completely flat, 0, because x2 is 0. And if x2 were negative, well then the effect of x1 on y is actually decreasing. So it would have a slope of -1. So this is a very challenging function because it makes no sense to talk about the effect of x1 on y without considering the effect of x2. The whole idea of an additive model is you can talk about the effect of one variable on y without considering the other variable. So I'm assuming these partial derivatives don't involve other variables, because that would imply an interaction. So what's going to happen? Actually, let me just show one more plot. This is an image plot that shows the height. So what you're going to see is blue is +1, pink is -1. And so you can see the saddle. This is coming up out of the page. This is coming up out of the page. The pink is going down into the page. So that's just another way to visualize this. Well, what would happen if we go fit a random forest on this? So it's quite a difficult function, impossible for just an additive model. Even for a random forest, this is not going to be easy. Notice I've added normal errors with a, this would have a standard deviation of 1/4. So the variance would be 1/16, or 0.0625. All right, I'm going to go build a random forest, and what you'll see is the variables are roughly equally important. What I'd like you to note is my mean squared error is pretty close to the nominal value. So the nominal value is 1/16, 0.0625. We're moderately close to that. Okay, so the random forest is doing a stellar job on this very difficult function. Well, let's go look at my partial plots. And so the partial plots make it look like there is no relationship. Okay, so what's the effect of x1 on y? It's basically flat. What's the relationship of x2 and y? Basically flat. So what's happening here is a partial plot is going to condition on some x value and average over all the x2 values. Well, for any x1 value, some of the x2 values will be positive, and those will be balanced out with values that are negative. All right, so all the positives balance out with the negative, except when x1 is 0, and in that case the function is completely flat. But when I've got the positives and the negatives balancing out, my averages, conditional on any x1, will be 0. So looking at the partial plot basically says, there's nothing happening here, when in fact there's a lot happening here It's just that we can't see it with this additive plot. So this kind of really brings into focus my third criticism of these partial plots, and that is, the partial plots implicitly assume you have an additive function. At least these partial plots do. I'm going to show you a slightly different version in a second. But if you really have an additive model, go fit an additive model, and use your splines and get your nice confidence bands on them. You don't really need these partial plots for understanding an additive model. And if you don't have an additive model, the partial plots break down, as we see here. Well, I do want to point out there are versions of the partial plot that can help you detect interactions. So the ALE plot implementation actually will allow you to do, to generate an image plot for, the interaction between two variables. And so if we go examine this image plot, you're going to see the estimated function is, there's some pretty complicated contours in here, but when you look back and squint a little bit, clearly you have the basic shape of a saddle, where you have high values on when both values are positive or both values are negative. You get extremely negative values. You can look at the values of your contours there when exactly one of the two variables is negative, and then this should be roughly 0 in the middle. All right. So that's it for my my lecture on these methods for interpreting a random forest or a bagged tree model.